In this video, we're going to have a look at some AS level bond angle and shapes of molecule questions. So these questions pop up all the time, even in proper A level papers, but especially at the AS level, so in the breadth and depth papers. But they follow you through all the way to the end. So it's one of these things where it's very much a case of, in terms of shapes, it's a memory game. It's about learning all the shapes and learning where they apply. In terms of bond angles, they're very, very straightforward to work out. And when they do come up on papers, they are simply worth far too many marks for how much work you have to put in for them. So it's really, really good to get, it's really a good idea to get confident with this, because in exams, they only ever ask questions in very much the same way every time, and it's free marks. It's just free marks. There are no catches to these questions, well, there are, but not particularly. Okay, once you've learned to spot the traps, it's much, much easier to avoid them, and you'll never get them wrong when you start getting them right consistently. It's really, really good to have a firm grasp of this going forward, because the questions are always asked in the same way, and it's so easy to get a high number of marks for very little work. So we'll quickly run through some of these questions then. So first question, sulfur hexafluoride, SF6. State the shape of and the bond angle in SF6. This is about as easy as the questions you could ask. You've got sulfur bonded to 6 fluorines. So if you want to know what that looks like, you've got sulfur bonded essentially 6 times. Now, if you did a dot and cross diagram here, you'd find sulfur has far too many electrons, but that's okay because it can have an expanded octet. Okay, so sulfur is one of those, elements, one of those many elements. When you get into period 3 and below, you can get an expansion of the octet thanks to the availability of the d orbital, which is now available to take electrons as well. So a very, very straightforward shape. Okay, you'll see this a lot in A2, particularly in the transition metals topic. The shape is octahedral. Okay, it is called octahedral because if you were to draw it as if you basically had it in a 3D, and you actually put is a 3D shape and you put faces onto the shape, it would be an octahedron. It would be 2 square-based pyramids inverted on top of each other. Okay, so it's, people say, oh, it's octahedral, but it's only got 6 bonds. It's because if you make the 3D shape and you actually connect all of the points up with actual faces, you would get an octahedron. And luckily for us, the bond angle is very, very straightforward. Every single bond angle in an octahedron is 90 degrees. Always will be. And you get 2 marks for very little work there. So, why is SF6 unreactive? Now, there's lots of reasons for this. Okay, there's not just one reason. Okay, so don't be fooled into thinking this is 1 mark. But in reality, you don't have to come up with much. Okay, you really just have to talk about things like the dipoles. Okay, it has no overall dipole. Okay, that would get you the mark on its own. So just saying, no overall dipole. Okay, just having no overall dipole is enough. It's not reactive. Okay, or you can say its covalent bonds are strong. Okay, either or, that will do. Okay, so there's no big thing with this question. It's got an overall dipole, so it's not going to be taking part in any mechanisms you know about, and it's got strong covalent bonds, hard to break, so not exactly an easy molecule to work with. Nice and straightforward. So, second question then. Common multiple choice, really common type of question, saying which one's got the largest bond angle, which one's got the smallest bond angle, something like that. You get 4 seemingly random molecules. So to do this, the best bet you've got is simply to draw it out. Okay, if you know what the compound is, even better. So C2H4, I'll do first. Okay, I'll put this one in blue. So C2H4, hopefully you'll realize is ethene. Now ethene, when we talk about the bond angle, we're only going to talk about the H to C bond angle. That's the only angle there really is. You can talk about the HCH bond angle, it's the same thing. Okay, all you got to do, pick one of the carbons, count the number of regions of electron density around it. So you've got 1 bond here, 2 bonds here, and the double bond counts as 1 because the electrons are all in the same place. So you've got 3 bonds, or 3 bonding regions, I should say, no lone pairs, and so this bond angle here is 120 degrees. Again, this is something you just need to learn, so forgive me if I'm not explaining this all too well, but this isn't the point of the video. If you need to learn the bond angles, you need to go back and look in a textbook to learn up on those. They're the same every time. 3 bonding regions of electrons, they all repel equally, so you get 120 degrees. So that's C2H4. Okay, so let's go for water next. Now, water is one of our, special cases, as it were. So water, if you draw it, has 2 covalent bonds to the hydrogen and 2 lone pairs. Please don't forget the 2 lone pairs, because it becomes vitally important now. Because in this bonding scenario, I've got 2 bonds, yes, but I also have 2 lone pairs. So I have 4 pairs of electrons in total. Now, all electron pairs will repel each other. So these 2 lone pairs cannot be ignored. Most people, some people, not most, but some people will look at this and go, oh, it's 180 degrees because I've got 2 bonds, they repel each other equally. These 2 electron pairs that are lone pairs are going to repel just as much, and actually more. So it's actually like you've got 4 bonding regions. Now, if you've got 4 bonding regions, normally it will be tetrahedral at 109.5. But lone pairs are localized. They stay in the same place. They don't move around the bond. So they are stronger at repelling. The upshot of this is that they reduce the bond angle by 2.5 degrees for every lone pair. So what should be 109.5, you end up subtracting 2.5 and another 2.5. So you end up with a bond angle of 104.5. Okay, this is a non-linear molecule, or bent, depending on how you were taught it. So that's pretty low bond angle, so that's probably not going to be our answer. Right. NH3 then has a similar issue. Okay, if we draw NH3, again, I'm not going to draw it all in 3D because it's not really worth it. NH3 has a lone pair and 3 bonds. So this is the same as water in the sense that it has 4 electron pairs. So the bond angle should be 109.5. However, this time it has 1 lone pair, and that 1 lone pair will distort the angle ever so slightly and take 2.5 off, which will give it a bond angle of 107 degrees. Again, not going to be our answer. And those who are eagle-eyed observers here will have seen that the final option is CH4, which is very, simply put, a straightforward 1, 2, 3, 4 bonds, tetrahedral 109.5. Therefore, the answer to the question is A, because that has the greatest angle at 120. This is why learning all these bond angles and shapes go hand in hand, because if you can work out the shape from the number of bonding regions, if the bond angle just goes with it. Okay, so it's definitely something you can just brute force learn, okay, without much effort. Final thing then, this is a diagram. They will give you drawings sometimes, and they will simply say to you, predict the shape of a molecule, and you've got to go for it. Sometimes they'll ask you to predict the bond angle as well. In this case, we've not got to do that, but it's the same thing really, and this is the main part of what we need to do now. So we're given a dot and cross diagram. I will point this out to you. Dot and cross diagrams and stick diagrams are not drawn to scale. Okay, that means you can glean absolutely nothing from what they have drawn. For example, I'll just do something completely different here, but if I drew methane out as if you were drawing it, as if you were drawing like a straight chain alkane, okay, most people would draw methane like this. That doesn't mean the bond angle is 90 degrees. The bond angle is still 109.5. It's just much easier to draw it like this because it's clear to everyone. Conversely, just because something is drawn flat, it doesn't mean it is. Okay, so again, if I have an alcohol group, for example, I might do C to O to H. That doesn't mean that it's 180 degrees. There's two lone pairs here. The angle's 104.5. But I'm not going to do that. I'm not going to show that because it's easier to draw it in displayed formula without drawing all the correct angles. So don't expect the examiners to be giving you any help here in terms of how they've drawn it. So name of the shape then. All you got to do, and this is the same as if you asked for the bond angle actually, the explanation is actually the identical thing. So you look at the central atom, okay, of SB, okay, antimony, and you count up the electron pairs. So there's 4 electron pairs total. So it's 4 pairs. Okay, 1 is a lone pair, and 3 are bonding. This is the analysis you should always do. So 3 bonding pairs and a lone pair, that means, well, first off, you've got 4 pairs, it means tetrahedral. 1 lone pair will change it slightly because of the extra repulsion, and so the shape is going to be pyramidal and not tetrahedral. So you've got pyramidal shape. Now the explanation is the same explanation that you would give if I asked you what the bond angle was. Okay, the explanation is always the same. Okay, and you should always write the same things. Now, first thing you should always write on any single one of these is electron pairs repel. So I'm just going to E minus pairs repel. There's sometimes a mark for that. It shows the examiner you know what you're talking about. So electron pairs repel. The next thing that picks up the marks is actually writing down what pairs of electrons you have. So literally writing 3 bonding pairs and 1 lone pair is good enough to get you a mark. Okay, and this is the same. Okay, if you asked what the bond angle was, I would answer the question in the same way. So if we pretend that says name, bond angle instead of shape, I'd be writing 107 degrees. I'd still be writing, for my explanation, electron pairs repel, 3 bonding pairs, 1 lone pair, and my final thing, lone pairs repel more than bonding pairs. Okay, simple. And it's the same explanation every single time. It never changes. If you always set out your explanation like this for a shape or a bond angle explanation, you will always pick up maximum marks, provided, of course, you count them correctly, but that's not the hard bit. Okay, electron pairs repel. I have 3 bonding pairs and a lone pair, and lone pairs repel more than bonding pairs. That's all you need to say. That gets you 3 marks every time. Okay, so stick that in your head as to how to answer this question. Okay, so get the name of the shape, get the bond angle, whatever they're asking for, state that electron pairs repel, that underpins the whole idea of shapes of molecules, state the number of pairs, bonding and lone, and then if there are lone pairs, not always lone pairs, if there are lone pairs, you say that lone pairs repel more than bonding pairs, and that's it. Take the 3 marks and move on with your life. So, SbCl3 molecules are polar. Okay, 2 reasons for this. Okay, there's always 2 reasons why something is polar. First of all, it's because you have a change in electronegativity. Okay, so there's an electronegativity difference, which will give rise to your delta plus, delta minus. Okay, and the second one, which is a really important one, is that the molecule is not symmetrical. Okay, if the molecule is symmetrical, then the dipoles cancel out. It cannot be symmetrical, okay? And it's not symmetrical because if you drew it in 3D, you would have Sb at the top, and you would have something like this. The Sb would be on the top, and the Cls would be on the bottom. So you'd have an overall change in dipole from top to bottom, because as you can clearly see if I draw a mirror line on, that ain't symmetrical. So there you go. Nice and straightforward for 2 marks. There's an electronegativity difference. You can write that Cl is more electronegative than Sb. That's fine. And the molecule is not symmetrical. So hopefully that helps you understand a little bit more about how to approach these types of questions, and in the best practice when it comes to answering questions based on, electron pairs and bond angles and shapes, because it's always the same explanation. And if you can get that right, it gets you loads and loads of marks.